Watch the complete playlist on the app PIONS. Download the app now.
Monochromatic light of wavelength 600 nanometer is incident from air on a glass surface. What are the wavelength, frequency and speed of refracted light? Refractive index is given as 1.5. Correct? So whenever a light ray is going from one medium to another medium, one thing doesn't change. And what is that one thing? Frequency. So frequency will remain same. Be very careful. The frequency of this refracted light is remained same. Okay, it won't change. Clear? So both the wavelength and the speed of light both will change. Clear it is? So first of all, frequency we can find. Frequency of the light will be equal to our speed of light upon lambda, where speed of light is speed of light in free space, right? So let me write here c upon lambda, and c is nothing but 3 into 10 to the power 8 meter per second, right? Whole divided by lambda. What is the wavelength here? 600 nanometer. In case if you are not familiar with nanometer, it's 10 to the power minus 9. Clear it is? Now 9 goes on the top. It will give you how much? 3 upon 600 into 10 to the power 9 and 8, 17. Clear it is? Now this will give you here as our approximately 5 into 10 to the power 14 hertz. So this will be our frequency. Okay, and this frequency remains same. Okay, clear? Now let's find the speed of the refracted light when it goes into another medium. So that will be our mu is equals to c by v. This formula we have seen in the previous problems also. So this will be c upon v. And what is c? C is 3 into 10 to the power 8 upon v. We are looking for this velocity in the medium. So v will be equal to 3 into 10 to the power 8 divided by mu. What's the refractive index? 1.5. That's equal to 2 into 10 to the power 8 meter per second. That's our speed in the medium. Clear? Now what will be the wavelength of the refracted light? Okay, we already have the speed and we have the frequency. So wavelength lambda in the medium will be equal to, let me call it as lambda prime, that will be equal to v upon frequency. Correct? So v is how much? 2 into 10 to the power 8. And what's the frequency? Frequency is 5 into 10 to the power 14. Okay, so when you divide, it will be 4 into 10 to the power minus 7, or you can simply make it 0.4 and 10 to the power, okay, in that way. So that you can write it as 400 nanometer, that is inside the medium. Let's start with our new question. It says white light consists of waves of wavelength between 400 nanometer to 700 nanometer. This is the range of the wavelengths, right? What will be the wavelength range if this light goes through water? Okay. So we know that if a light ray travels inside the water or any other medium, its wavelength and speed changes. But what remains same? Frequency. Always keep in mind. So let's find what will be the wavelength in the water. That will be equals to wavelength in the air whole divided by refractive index of the water. Okay. So that will be nothing but 400 divided by 1.33. And when you divide, it will be approximately 300 nanometers. Okay. Similarly, the highest range is 700. So this is the lowest range. Highest range in the water will be 700 divided by the refractive index of the water. And that will be approximately 525 nanometers. Clear? So no need of conversion into 10 to the power minus 9. And anyways, you will get the wavelength in nanometers only. So in water, the same range is from 300 nanometers to 525 nanometers. Done. Let's start with next one. The question says two plane monochromatic waves propagating in the same direction with amplitude A and 2A are differing in phase by pi by 3 superpose. Okay. So this is pi by 3 is our phase difference. Calculate the amplitude of the resultant wave. So we know that the amplitude of the first wave is A1, that is equals to A, and amplitude of the second wave is A2, which is equal to twice of A. Correct? Now what will be the amplitude of the resultant wave? It will be equals to root under A1 square plus A2 square plus 2 times A1 A2 cos of angle phi. Clear? Now here if we substitute, this will give us how much? A square. Okay. Now be very careful. Amplitude square is intensity. So this formula can be used for intensity also. Okay. So that we will see later. So A square plus A2 square, 2A square plus 2 times A into twice of A into cos of pi by 3. Pi by 3 is 60 degree. And what is cos 60 degree? Half. So let's put it here. Root under A square plus 4A square plus 4A square into cos 60 is half. So this 4 and this 1, 5A square and plus 2A square. So this will be root under 7A square. This will be the resultant, okay, amplitude. So let me write here A resultant, otherwise you will get confused between A1 in this A and that A. So A resultant will be equal to root 7A. That is our A resultant amplitude of both the monochromatic waves. Let's solve this question. So our question says, two sources of intensity I1 and 4I1 are used in interference experiment. Find the intensity at point where the waves from the two sources superimpose with a phase difference 0, pi by 2 and pi. So before we apply this phase, okay, let me write the formula for resultant intensity. That will be equals to I1 plus I2 plus 2 times root under I1 I2 cos of angle phi. Correct? Now what is our first intensity? I1 is given as I and I2 is given as 4 times I. Let's substitute in the above relation. So IR will be equals to I plus 4I plus 2 times root under I into 4I and into cos of angle phi. Correct? Now I plus 4I, 5 times intensity, plus now this 4 root is coming out and it will make it 4, and I square will be I. So 4I cos of angle phi. This will be our resultant intensity. And let's put now different values. So first one, if phi is equals to 0, cos 0 is 1. And in that case, the resultant intensity will be 5I plus 4 times cos 0. Cos 0 is 1. So that will be our 9I. Correct? The second one, phi is equals to pi by 2. And what is cos 90? Cos pi by 2 is 0. And if cos pi by 2 is 0, then resultant intensity at that point will be 5I only, because the second term will reduce to 0. Right? Cos phi. 4I cos phi will be 0. Third case, phi is pi, and if phi is pi, so cos pi is nothing but minus 1, and if cos pi is minus 1, the resultant intensity IR will be equals to 5I plus 4I and into minus 1. Cos phi is minus 1, so 5I minus 4I is I. So resultant intensity is I. This is the third one, this is the second one, and this is the first one. Done. Okay, let's see the next question. Question says, in Young's double slit experiment, the two parallel slits are made 1 millimeter apart. Okay, so the slit separation small d is 1 millimeter. 1 millimeter is nothing but 1 into 10 to the power minus 3 meters. Okay, apart. And a screen is placed 1 meter away. So capital D is nothing but 1 meter. What is the fringe separation when the blue-green light of the wavelength 5 nanometer is used? So lambda here is 500 nanometers, 10 to the power minus 9 meters. Correct? Now you have to find the fringe separation. Now those who don't know what is fringe separation, it is same as fringe width. So fringe width is fringe separation, and it is given by beta, which is equal to lambda d by d. And what is lambda? 500 into 10 to the power minus 9. D is nothing but 1, and small d is nothing but 1 into 10 to the power minus 3. If you take 10 to the power minus 3 on the top, it will be 500 into 10 to the power minus how much? 6. And this will be 5 into 10 to the power minus 4. Done. That will be in meters. That is the fringe separation. Let's start with our next question. It says, a laser light of wavelength 630 nanometer incident on a pair of slits to produce an interference pattern in which the bright fringes are separated by 8.1 nanometer. A second light produces an interference pattern in which the fringes are separated by 7.2 millimeter. Okay. So one is 8.1, it's typing error, it's millimeter, okay? It's not nanometer, it is millimeter here, okay? So, and the second one is producing 7.2 millimeter. Calculate the wavelength of the second light, okay? So basically what we will do here is, we will take beta. Beta will be equals to how much? Lambda d by d, correct? This is our fringe separation. Now in the first case, wavelength is how much? 630 nanometer, okay? And what's the fringe separation? Beta 1 is 8.1 millimeter. The second light, we don't know what is lambda 2. And fringe separation beta 2 is 7.2 millimeter, correct? Now rest other things are not changing as per the question. They remain same for the same, okay, system. So beta 1 will be equals to lambda 1 d by d. And beta 2 will be equals to lambda 2 d by d. If you divide equation 1 with equation 2, what will you get? Beta 1 upon beta 2 will be equals to lambda 1 upon lambda 2, correct? And this implies lambda 2 will be equals to lambda 1 into beta 2 upon beta 1. And what is lambda 1? 630 nanometers. So let's put it 10 to the power minus 9. And beta 2 is how much? 7.2 millimeter. So 10 to the power minus 3. Beta 1 is 8.1 millimeter, 10 to the power minus 3. Let's cancel this 10 to the power minus 3 with this. Let's remove this decimal with this. So 9 8s are 72, 9 9s are, okay, and 9 7s are 63, 8 7s are 56. So 560 into 10 to the power minus 9 meters, or 560 nanometers. That's our answer to this problem. Done. Let's move to our next question. Our question number, next one says, in Young's double slit experiment using light of wavelength 400 nanometers, so lambda here is 400 nanometers, interference fringes of width x are obtained. So beta is nothing but x here, correct? The wavelength of light is increased to 600. So let me call it as lambda 1. Lambda 2 will be equal to 600 nanometers. And the separation between the slit is halved. So if the separation between the slit is here d, here it will be d by 2. If one wants the observed fringe width on the screen to be same, so here also it is x. So beta 2 is also x and beta 1 is also x. Find the ratio of the distances between the screen and the plane of interfering source in the two arrangements. So you have to find the ratio of d1 and d2. Let me write the formula now. So beta 1 will be equal to lambda 1, okay, into d1 upon small d, correct? And beta 1 is nothing but x, which is equal to lambda 1 d1 by d, equation 1. And what about beta 2? Beta 2 will be equals to lambda 2 into d2 upon d by 2, because it's halved. So beta 2 is nothing but x, which is equal to lambda 2 d by 2. So 2 goes on the top. Now equation 1 and equation 2, the left hand side is same. So can we write for equation 1 and 2? Right hand side must be same. From 1 and 2. Lambda 1 d1 upon d is equals to twice of lambda 2 d2 upon d, correct? Now d can cancel both the sides, correct? So d1 upon d2 will be equals to twice of lambda 2 upon lambda 1. Let's substitute here values. So 2 times lambda 2 is 600 nanometers, 10 to the power minus 9, upon lambda 1, that will be 400 into 10 to the power minus 9. Let's remove this, cancel out this with this, this with this, this with this. You're left with 12 by 4, which is 3 by 1. So the ratio of both the separations is 3:1. Done. The question says, if two slits in Young's double slit experiment have width ratio 4:1, the width ratio of the slits, okay, is 4:1. Deduce the ratio of intensity at maxima and minima in the interference pattern. Very important. Okay, previous year question it is. So here we should know that the amplitude ratio, let's call it as R. This will be nothing but the ratio of amplitude in the through the first one and through the second slit, right? A1 upon A2. and amplitude is nothing but root of intensity. So root of first intensity I1 upon root of second intensity I2. Okay, and root of first intensity is nothing but root of width of the slit W1 upon root of width of second slit W2. Okay, and this ratio is given how much? 4:1. Correct? So we can find, okay, sorry, this root of 4 width ratio is given, no, 4:1, right? So this is nothing but 2:1, which is 2. So our amplitude ratio is given how much? R is equals to 2. This is very important, amplitude ratio, the ratio of the two amplitudes. So the intensity, maximum intensity divided by the ratio of minimum intensity, they are asking. Maximum intensity will be equal to what? The ratio of amplitude R plus 1 upon R minus 1 whole square. Okay, so this will be nothing but 2 plus 1 upon 2 minus 1 whole square, and that's 2 plus 1 3, 3 square is 9, so 9:1. That's our complete answer to this question. Let's move to the next question. The question says the ratio of intensities at minima to the maxima in Young's double slit experiment is 9:25, which means the ratio I minimum to I maximum, that is given here as 9:25. Find the ratio of their widths of the two slits. Correct? So we know that I min upon I max, that is nothing but R minus 1 upon R plus 1 whole square. Correct? So square here and square here. Now if you find the root both the sides, R minus 1 upon R plus 1, that will be equals to nothing but 3:5. Taking the root both the sides. Correct? Now this, when you cross multiply, we can find the value of R. So 5R minus 5 equals to 3R plus 3. And this will be 2 times R equals to 8. R is equals to 8/2, which is 4. Sir, what is R? R is amplitude ratio, the ratio of the two amplitudes. Correct? So R must be equals to, 4 must be equals to A1 by A2. That's the ratio of amplitudes. Correct? And if A1 upon A2 it is, that is nothing but how much? Root of I1 upon I2. And that is nothing but root of W1 upon W2. Correct? Amplitude ratios will be root of intensity ratios. Be very careful. I1, I2 are intensities. And I min and I max, that's the maximum and minimum intensities. Root of W1, width of the first and the width of the second slit. Correct? So now let's take the last part. So 4 will be equal to root under W1 upon W2. And when you square both the sides, this gives you W1 upon W2 is equals to 16:1. Or this implies W1 ratio with W2 width is 16:1. Done. This is our complete answer. Let's do the next question. Question says, what is the frequency of a photon whose energy is 66.3 electron volt? So here we are given with the energy. The energy of the photon here is 66.3 electron volt. Be very careful, you are given with electron volt. So whenever you are finding the frequency, you will have to, frequency, wavelength, anything they are asking, you will have to convert this electron volt into joules, because electron volt is not our standard, okay, unit. So 66.3 into 1.6 into 10 raised to minus 19, okay, that will give you energy in joules. Once you get the energy in joules, we know that E equal to H nu. So nu equals to E by H. Sir, what is H? H is Planck's constant. So it will be 66.3 into 1.6 into 10 raised to minus 19 whole divided by 6.63 into 10 raised to minus 34. Let's remove this, okay, you will get 100 here. Let's remove this, you will get a 10 here, and then let's cancel these two. So 110, let's cancel these two. Now you left with frequency, which is 1.6 into 10 to the power. Now minus 19 and plus 34. That will give you how much? 14 minus 9. That will give you 5, and 2 minus, okay, 1, which is 1. Okay, plus 15 into 10. So that will be our frequency equals to 1.6 into 10 raised to 16 hertz. That's our standard unit. Done. Okay, let's move to our next question. Question says monochromatic light of frequency. What's the frequency here? That is given as 6 into 10 to the power 14 hertz, okay, is produced by a laser. The power emitted, now power emitted here is 2 into 10 to the power minus 3 watt, correct? The question they are asking is what is the energy of each photon in the light, and the second part is how many photons per second on the average are emitted by the source. Clear? We know for the first part energy is nothing but h into nu. So h is Planck's constant 6.63 into 10 to the power minus 34 multiplied with frequency. What is the frequency? 6 into 10 raised to 14, correct? Let's multiply them. 6 3 is 18, 6 is 36, 7, 6 is 36, 37. So 37.78 into 10 to the power minus 0 and minus 3 minus 1, 2, minus 20 joules. That will be a energy, correct? So 337.78 into 10 to the power minus 20 joules. Done. Now they are asking how many photons are emitted per second on the average, okay, from the source. So second one is we have to find the number of photons. So number of photons is always equal to the amount of power emitted by the source upon the energy of each photon, right? So power is how much? 2 into 10 to the power minus 3 whole divided by 37.78 into 10 to the power minus 20. And when you will divide both, that will give you approximately 5 into 10 to the power 15, okay, photons per second. Okay, so this is our complete answer to this question. Let's see the next one. Our next question says for a photosensitive surface work function is given as this. What is work function? Phi. So phi is given as 3.3 into 10 to the power minus 19 joules, correct? Taking Planck's constant to be h equal to 6.6 into 10 raised to minus 34. Find the threshold frequency. Now we know that there is a direct relation between work function and threshold frequency. So work function phi is h nu naught, where nu naught is our threshold frequency. So nu naught will be equals to our phi upon h. What is phi? Work function, which is 3.3 is the work function. So 3.3 into 10 raised to minus 19 whole divided by 6.6 into 10 raised to minus 34. So 3.3 and 6.6, that will straight away cancel out and you left with half, and okay, so we'll cancel from 3 11. Okay, let's remove this with this. 11 3s and 11 6 and 3 by 6 is 1 by 2 into 10 to the power how much? It is minus 34 goes up, so it will be 14 minus 9 5 and 2 minus 1 15. Okay, 15, and that is nearly 0.5 into 10 raised to 15, or you can write it as 5 into 10 raised to 14 hertz, correct? This is our threshold frequency.
Watch the complete playlist on the app PIONS. Download the app now.